KAWAKAMI from Weekend Japan. First of all, I'd like to thank the organizer for giving me this opportunity to give a talk titled Floating Electrons as Qubit. We like to use floating electrons as qubit. So we like to make qubit out of electrons floating on the surface of helium. So first of all, I would like to tell you why we like to use electrons as qubit. First, electrons are light, and so it is easy to move electrons. And so we can transfer qubit from one place to another place. We can also realize some qubit functionalities by modulating the electron's position. So it's nice to have a light qubit. Second, electrons are small. So if we would like to increase the number of qubits, if you like to scale the qubit, scale up the number of qubits, it's better to have a smaller qubit. And third, the electrons have both electric properties and magnetic properties, charge and spin. An orbital state is an electric quantum state, and the spin state is a magnetic quantum state. So orbital state tend to have large interactions, and the spin state tend to have small interactions. If the interaction is small, the coherence time tends to be long, but it is with a smaller interaction, we can realize only a slow control of the qubit state. On the other hand, the orbital state tend to have a short coherence time, but if the interaction is large, we can realize a fast control of the qubit functionalities. So there are pros and cons on the both sides. And so using the electrons, we can make the best of the both worlds. That is why we like to use electrons. So I think we can categorize physical systems of using electrons as qubits into two categories: electrons in solid and floating electrons. So in the left case, the electrons exist in solids, such as diamond or semiconductors. In the right case, the electrons exist in vacuum. That is why we call them floating electrons. Here I show you the trapped electrons. So that electron is trapped almost in the same way as ion trapped. And so this, the other one is called the electron on helium. Today I would like to talk about the electrons on helium because this is what I'm working on. So the research on using electrons in solids as qubits advanced a lot recently. And on the other hand, the research on floating electrons on helium did not progress so much in terms of the quantum computation. So why didn't it make so much progress? I think one of the reasons is that compared to the electrons in solid, it is not easy to access floating electrons. And so it means that it is not straightforward to read out the electron state. But what is the advantage of using electrons on helium as a qubit? Why do we like to try to use them? Electrons exist in vacuum, which means that we do not have any defect or impurities around them. So it is a very clean system. We can expect to have a long coherence time. So let me explain you more about what I mean by the system is clean. For example, when the electrons are prepared in semiconductors, for example, in silicon, electrons are exposed to noise induced by the defect or impurities of the silicon crystal. On the other hand, the floating electrons on the surface of liquid helium exist in vacuum, so they are free from the defect or impurities. So, but what is the downside of the electron of helium? It is not straightforward to read out the electron state. So if you look at what is happening for electrons in semiconductors, the the one single electron is trapped here, and we can have a huge current running close to this electron, and by measuring this current, we can tell the quantum state of this electron. But we cannot do the same thing for the electrons of helium because the electron floats in vacuum, and we cannot have the ohmic contact to the floating electrons. So that is the problem of the electrons on helium, I think. So here, let me show you the history of electrons on helium. So in 1969, it was theoretically demonstrated that a stable two-dimensional system can be created on the surface of liquid helium. And following this theoretical proposal, they measured a two-dimensional electron system formed on the surface of helium in 1972. And in 1976, a quantum state of electron helium was measured for the first time. This quantum system is called the Rydberg state. I will explain you what is the Rydberg state later. In 1999, our first theoretical proposal of using electron on helium as qubit was published. And in 2005, a single electron was trapped on the surface of helium for the first time. So we would like to make a single electron as a qubit. So this was an important step. I may need to emphasize that the spin state of the electrons of helium have not been measured yet, and any qubit functionality has not been realized yet using electron on helium. So there are many things that should be done using the electrons on helium. Okay, so I would like to briefly explain you the why electrons can float on the surface of liquid helium. So first, we should prepare the liquid helium, of course. So the helium stays liquid if the temperature is lower than 4K, so we should cool down the liquid helium. So the point of using the liquid helium is that the relative permittivity of liquid helium is a little bit higher than 1, and the electron affinity of the helium is negative. And Cole and Cohen predict that two-dimensional electron system can be formed on the surface of a material of which relative permittivity is higher than 1, and the electron affinity is negative. So other materials which satisfy these conditions are solid neon and solid hydrogen. Surface electrons on solid neon and solid hydrogen were also measured already, and recently making qubits using electrons on solid neon was very successful. So if you are interested in, please read this paper. So let me continue to explain you why electrons can float on the surface of helium. Since the helium's relative permittivity is a little bit higher than 1, when the electrons approach the surface of liquid helium, it induces a positive image charge at the same distance from the surface as the electron itself. The image charge can be written with this equation, and then the force induced by this image charge on the electron is described here, and the potential felt by the electron can be written with this equation. Now, okay, so this electron is attracted to the liquid helium, but it cannot enter into helium due to the negative electron affinity. If the electron enters into liquid helium, it makes the helium atom unstable. So the electron feels a barrier, 1 electron volt, at the surface of liquid helium. So in total, the electron feels this kind of triangular potential as shown in this figure. And so this potential is described with this equation. So we just need to solve the Schrödinger equation. And if you solve the Schrödinger equation, and then you can find this kind of condensed energies. And so this part is the Rydberg constant. So for the hydrogen, so you can write down, so this is a Schrödinger equation for the hydrogen atom, and here you can find the Rydberg constant, so it's the same Rydberg constant. So the difference between this equation and this equation is that for the hydrogen atom, it's a 3D confinement, and for the electron on helium, it's 1D confinement, and we have some constant here. So that is why we call this quantile state normal to the surface liquid helium Rydberg state. So here in this figure, I plotted the probability density of the wave functions. So the blue curve is the probability density of the Rydberg ground state, and the average position of the Rydberg ground state is 10 nanometer away from the surface of liquid helium, and the orange curve is the probability density of the Rydberg first excited state, and the average position of the Rydberg first excited state is 13 nanometer away from the Rydberg ground state. So now the confinement is only along Z, normal to the surface of liquid helium. So the electrons can move freely along X and Y. So the two-dimensional electron system is formed 10 nanometer above the surface of liquid helium. So if there's if there's a confinement only along Z, we cannot control electrons individually, but we want to use a single electron as a qubit, so we need to confine the electrons also along X and Y directions. And so we need to localize the electron in one place. In principle, we can make this kind of electrons, so this kind of electrons, and then if we apply negative voltage on this big electron, we can deplete the electron on top of these electrons, and then we can apply a positive voltage on this electron, and we can accumulate the electron here. So this is how we trap a single electron here. But okay, so the real device looks more complicated than this. So these two figures are the real devices. So in 2005, they have succeeded in trapping a single electron on helium for the first time, and also recently the Chicago's group also succeeded in trapping a single electron. Okay, so but now, so the question is that, so which quantum state should be used as qubit state? So I already showed you that we can have the Rydberg state, but of course this is the electron, so we can also have the spin state. So which one is better? So there are pros and cons of using Rydberg state and spin state. So the advantage of using Rydberg state as a qubit is that the Coulomb interaction, the interaction which connects the Rydberg state is very large. Even if the two electrons are separated by 1 micrometers, the interaction is still high. And however, the coherence time of the Rydberg state is short, only 1 microsecond. So for the spin state, the interaction is small. So the interaction is a magnetic dipole-dipole interaction is very small. Even if we place the electrons very close, like the distance is 100 nanometers, the interaction is 100 Hz, super small. But the advantage of using the spin state is the long coherence time. And so that's why we propose to make the hybrid qubit of the Rydberg state and the spin state. So for example, if we want to read out the qubit state, we transfer the qubit state to the Rydberg state, and so the interaction is large, so we can read out the state easily. And if we want to use the, if we want to store the qubit state, we transfer the qubit state to the spin state, and we can benefit from the long coherence time. So that was our theoretical proposal. We are writing a paper on that right now. But so to transfer the qubit state between the Rydberg state and spin state, we need to have an interaction between the Rydberg state and spin state. We don't have such an interaction intrinsically, so we should create an artificial interaction. So if we make the interaction between the Rydberg state and the spin state, we open the path for the relaxation of the spin state via the Rydberg state, and then the coherence time becomes a little bit shorter, but it's still long enough. So here I show you how we can realize an artificial interaction between the Rydberg state and the spin state. So for example, we can make this kind of cylindrical electrode, and we can fabricate this cylindrical electrode out of ferromagnetic material, and then we apply static magnetic field along that axis, and then this ferromagnet is also magnetized along the same direction, and then we can get the stray field out of this ferromagnet. And now the position of the Rydberg ground state is around 10 nanometer away from the surface of liquid helium, and the position of the first excited state is 20 nanometer away from the ground state. And so depending on the Rydberg state, the electron field different magnetic field. So it can have a different Zeeman splitting. And so it creates the interaction between the Rydberg state and the spin state, the Rydberg spin interaction. So to realize the qubit functionality, we would like to use these four states. So here we have the ground Rydberg state and the first excited Rydberg state. And if we apply a static magnetic field, we can have the spin up state and spin down state for each Rydberg state. So we would like to use these four states. Yeah, sorry, I didn't explain you this before, but as I wrote here, so we would like to have a cylindrical electrode, and we want to line up these cylindrical electrodes with a distance of 1 micrometer, and the electron can be trapped by this cylindrical electrode, and so the one electron can float on top of this cylindrical electrode. So this is just our proposal. So in order to claim that we can make qubit out of electron of helium, we should demonstrate qubit functionalities. So these three qubit functionalities: read out of the qubit state, and universal 1 qubit gate, and the 2 qubit gate. So so for the universal 1 qubit gate, it is almost the same as what quantum community is doing. So I don't want to go into the details today, but I like to show you how we plan to read out the qubit state, or we also did some experiments. So I like to show this one, and I also like to show you briefly how we can realize the 2 qubit gate. So as I already told you in the beginning, so in semiconductors, the electron in the semiconductors, the state of a trapped electron can be read out by measuring the current running near the electron. But we cannot do the same thing because we cannot have the ohmic contact for the floating electrons. So how do we want to do is that we want to read out the quantum state of the electron capacitively. So we have this cylindrical electrode, and this electron is capacitively coupled. So if the electron's state is changed, this capacitance is changed. And by measuring this capacitance change, we can read out the electron state. So let me explain you how we can read out the Rydberg state capacitively. So Rydberg state is one of the quantum states. So in the end, I would like to show you we can also read out the chat. Why do I expect the T? Okay, okay, can I answer the okay, can I answer the question later? Sorry. So I would like to show you how we can read out the one of the quantum state of electron or helium. So let's consider this situation again. So we have the cylindrical electrode here, and when the electron is in the Rydberg ground state, the electron position is 10 nanometer away from the surface of liquid helium, and then this electron induces some amount of image charge on this cylindrical electron. Let's say that this electron induces Q here, and then we can excite the electrons by applying a microwave. And so field frequency is equal to the energy difference between the ground state and first excited state. Typically, it's around 200 gigahertz. And then the electron moved its position by 30 nanometers. Then electron is now the distance between the electron and the cylindrical electrode becomes further away compared to the situation here. And then now the induced image charge on the cylindrical electron is Q plus delta Q. So actually this delta Q is negative because the electron became further away from the cylindrical electrode. So if we measure this image charge change delta Q, we can know that the Rydberg transition happened. So how can we do that? So we connect an inductance to this cylindrical electrode. And then, so thanks to this capacitance, together with this inductance, we can form an LC inductance. And so we continuously apply a resonant 200 gigahertz microwave, and then the electrons move up and down, so between the Rydberg state and Rydberg ground state and Rydberg first excited state. And then the average position of the electrons over time is in the middle of the ground state and first excited state. And now here we apply AC voltage to this LC circuit, whose frequency is almost equal to the LC resonance frequency. And we can get an AC voltage drop here. And then the electron also feels electric field change. And due to this electric field change, the resonance condition is changed because of the Stark shift. And then if the resonance condition is changed, and then the position of the electron, the average position of the electron is changed. If the average position of the electron is changed, the amount of induced image charge on this cylindrical electrode is changed. And then this image charge change can be written with this expression, delta Q times sine omega LCT. And then, as you know, the charge is equal to the capacitance times voltage. And so this delta Q is equal to delta C times V0 here. And then this delta C is an AC capacitance change. So by measuring this AC capacitance change, we can detect the Rydberg transition. So now I would like to explain you how we can detect the spin state. So as I already explained you, we can have the straight field and then the electron feel the different magnetic field. So depending on the Rydberg state, the electron feels a different magnetic field, and it also has a different Riemann splitting. So in other words, depending on the spin state, it can also have a different Rydberg transition energy. So if the electron spin state is down, then we need to apply the microwave field frequency corresponds to this energy difference. But if the spin is up, this energy is different from this energy when the spin was down by 140 megahertz. So if we apply the microwave whose frequency corresponds to this energy difference, and then we can have the capacitance change only when the spin state is down. So this is our plan. Okay, so this is our plan. Okay, let me show you about the 2-qubit gate. Okay, so for the 2-qubit gate, so first I would like to talk you about the 2-qubit gate of the Dirichlet state, not the spin state yet. So for the 2-qubit gate of the Dirichlet state, so we like to use the Coulomb interaction. So Coulomb interaction is large, so even if 2 electrons are separated by 1 micrometer, we can still have around 100 megahertz, and we have this kind of term. So using this kind of term, we can realize a 2-qubit gate, a control not gate easily. And then we can transfer the spin state of the Dirichlet state. So as I explained you here, so we can transfer the spin state to the Dirichlet state using this microwave. So if this microwave is pi pulse, and then we can transfer the spin state to the Dirichlet state. So this is how we would like to transfer the 2-qubit gate of the Dirichlet state into the so we want to realize the 2-qubit gate of the spin state out of the 2-qubit gate of the Dirichlet state using this transfer. So so more concretely, so the controlled phase gate of the spin state can be realized with this pulse sequence. So we have pi pulse to pi pulse and pi pulse, but all the microwave pulses here are applied for the Dirichlet state. So it's a little bit complicated, but if you are interested in, I can explain you later. Okay, so that was our proposal. So we have 30 minutes left. So okay, so I don't have time to go into the detail of the experiment, but so this is how we generate the electrons. So if you are interested in, please ask the question later. So let me talk to you about our experimental progress now. So as I already told you, so this is about the readout technique. So we are working on the readout technique, and later we would like to work on the 1-qubit gate and 2-qubit gate. So for the readout, first the electron position should be changed by applying a resonant microwave for the Dirichlet state. And if the electron position is changed, the image charge on the electrode is changed, and the AC capacitance is changed. And so if the AC capacitance is changed, the LC resonance frequency is changed. So we are working on this kind of readout technique using many electrons on helium. And so this is what I did during my postdoc. And so after I moved to Weekend, so I'm working on this part. So unfortunately, we are still working on many electrons, and we should also work on reducing the number of electrons, and we need to realize this for a single electron. But let me show you about the experiment. So we have this kind of parallel plate capacitor. So it's actually a big capacitor. The area of this capacitor is around 1 centimeter square, and we can trap 10 to the power of 7 electrons between these capacitors. And this capacitor is capacitance of this capacitor is around 0.7 picofarad. And so on top of this capacitance, we put this inductance. So sorry that this circuit looks complicated. What is important is that we have the inductance here and we have the capacitance here. So we can have the LC circuit. And we also have a Baracta diode, which serves as a variable capacitance. And by changing the voltage applied to this Baracta, we can change this capacitance here. Okay, so I wrote the capacitance sensitivity here, but I don't have time to talk about capacitance sensitivity. Okay, so let me talk here about our experiment. So first, we apply the AC voltage to this point, and then if we so the voltage amplitude was 1 volt and the frequency was 100 hertz. So if we apply this kind of voltage here, and the voltage across to this Baracta diode is modulated at 100 hertz, and then so I just wrote here what I told you. So this is the capacitance modulation, and we found that this 1 volt corresponds to 0.012 picofarad. And so this modulation happens at 100 hertz. And then from this side, we inject the signal whose frequency is almost equal to the LC resonance frequency, which was 81.222 megahertz. So this is directional coupler. So we can get the reflected signal, but because we have this modulation here, the capacitance is modulated at 100 hertz. So the reflection coefficient of this LC circuit is modulated at 100 megahertz, and so the amplitude of this reflected signal is also modulated at 100 hertz. So this is what we measure. So sorry. So I just told you what we are doing, but we have liquid helium here, but we don't have electrons yet. Okay. So if we have the amplitude modulated signal, we can then we plug that signal into the spectrum analyzer. We can have this kind of side peak. So by measuring this side peak, we can measure the capacitance sensitivity. So this is a little bit complicated equation, but if you read this paper, you will understand why we can measure the capacitance sensitivity in this way. Okay, but in any case, we measured 300 attofarad at 2 Kelvin and then 30 attofarad at lower temperature, and which is just enough to detect the Liebeck transition of a single electron. So we are happy about that. And now, so we deposit the electrons, 10 to the power 7 electrons here. So now, we don't use this Baracta diode anymore. We apply a resonant microwave. So by the way, this is a conventional Liebeck transition peak. So by changing the voltage applied to this bottom electrode, we can see some peak here. So due to the AC Stark shift, so here we fix the microwave frequency due to the AC DC Stark shift. We can see the peak here when the voltage applied to the bottom electrode was 25 volt. We see the peak, and then now, so instead of a continuous microwave, we apply frequency modulated microwave, and the modulation frequency is 100 hertz. And the deviation of the frequency is 384 megahertz. But we use the same microwave frequency, so it was always 137 gigahertz. So if we modulate the frequency of this resonant microwave, it's the same as we modulate the resonance condition here. So now if we modulate the resonance condition here, then the average position of the electrons are also modulated at 100 hertz, and the image charge induced on the top electron is also modulated at 100 hertz, and the capacitance is also modulated at 100 hertz. And then so here we inject the signal whose frequency is almost equal to the LC resonance frequency of this circuit, and then the same as before, the reflection coefficient is also modulated at 100 hertz, and then we get the amplitude modulated signal, AM signal. So this is our measurement result. So this is what we measured on the spectrum analyzer with the frequency modulation on and frequency modulation off. The microwave was always on. So so we swept the voltage applied to the bottom electrode, and so we have observed the signal 100 hertz away from the center frequency, 81.222 megahertz, and we have seen this signal only when the voltage applied to the bottom electrode was tuned to the resonance with 137 gigahertz microwave, and we didn't see any signal when the frequency modulation was off. So we were so happy that we could demonstrate our idea using many electrons on helium. But now we would like to move to a single electron. So we were fabricating this. We are fabricating this kind of sample, and we want to make an LC circuit for a single electron. And so later we would like to scale up the number of electrons, and then we would like to realize a quantum computer using the electron of helium. So thank you so much for your interaction. And I found there were some questions there. Why the expected T2 star is sorry, by the T2 star. T2 star.
So we take questions now.
Sorry, so the why the expected T2 star is here, the T2 star. You mean that it's strange that T2 star is longer than T1? I understand that. Okay, sometimes it happens. It depends on the physical, the physical system. In our system, T2 can be longer than T1. And so before introducing the interaction between the Dirichlet state and spin state, both T1 and T2 are 100 seconds, but due to the interaction between the Dirichlet state and spin state, T2 star stayed 100 seconds, but T1 is reduced to be 100 milliseconds. Is it okay? Do you also do the experiment to read out spin states? Not yet. We like to do that, but we need to fabricate the sample with which we can do such an experiment. Thank you for your question.